Okay. Yep. So today we're going to be talking about GIMME, group iterative multiple model estimation. Okay, so GIMME is a modeling technique for network analyses, and we're thinking about networks, we're thinking about time series, and I imagine most of us, if not all of us here, are probably thinking in the fMRI realm. This would also apply to EMA data, or really anything that involves intensive time series. And the idea of GIMME, as we'll get into a little bit more, is that it's really purposed to kind of account for sample heterogeneity. We'll explain what that means, to derive ultimately some more individually precise networks that really reflect the individuals rather than groups, as those can be quite noisy. I learned most of this from a GIMME workshop taught by its creator, Dr. Katie Gates, part of the PIT Summer Methods series. And as in the Markdown document we'll get to eventually, I do have a bunch of links to some of the existing resources. And I do really encourage anyone that ends up using GIMME to really utilize these resources, because GIMME is really well documented both on the R package and Katie Gates's website. So we're going to start with some background on time series networks, heterogeneity, and this thing called ergodicity. I'm going to introduce GIMME and kind of walk through quickly how it works. And then the second half of the workshop, we might take a break before that, we'll be actually walking through using GIMME in R and some downstream analyses you can do with that. So we'll cover data formatting, running GIMME, some things you can do after that and stuff like that. And I'm going to be just probably only talking about fMRI. But if someone else interested in like EMA or something, just put that in the chat so I can keep that in mind, because I'm presuming most of us here are all thinking fMRI for now. But let me know if not. Okay. So background. So again, we'll be talking about intensive time series data. And when we say intensive, we don't mean 5 time points over like a year. We mean lots of time points. So multiple times a day in EMA or in fMRI, we have those 2-second TRs, right? Or we have a TR of 2, TR of 1. We get X hundred of those in a single scan. That's an intensive time series, our bold signal, let's say, for an ROI. And what a network does is it just defines interrelationships between these variables over time. And we're going to be using terms called nodes and edges. So in fMRI, nodes would be our regions, and each region, like a striatum, would have a time series of bold signal. And edges are just the associations between multiple nodes. So we could have a striatum and POC, 2 nodes, and they would have some sort of edge connecting them. So nodes are just your variables, and they have a time series, and edges are just the relationships between 2 different nodes of time series. Within those networks, they can be undirected versus directed. Undirected is probably what most of us are used to. So if we calculate a functional connectivity network, let's say using CON or SPM or FSL, things like that, generally it's undirected, right? It's just a strict correlation value between 2 different nodes. Conversely to that, we can have these things called directed time series networks, which they try to infer some directionality in them. And if we say in the fMRI world, this is when we're thinking about effective connectivity rather than functional connectivity. With the main difference being that with effective connectivity, the directional networks, we're hypothesizing an overall model that underlies the observed correlations and kind of test how well this hypothesized model fits the actual data. And if anyone's done work with DCM, dynamic causal modeling, that's effective connectivity. There's numerous ways to think about that. In the GIMME realm, we're going to think about Granger causality, which is really just trying to account for variance explained after accounting for the own node's autocorrelation. That gives us some directionality. And another main difference between these undirected, directed, particularly in the connectivity realm for fMRI, is in functional connectivity, we're considering each set of nodes completely independently. So we correlate X and Y, X and Z, Y and Z, all those are independent. And then this more comprehensive directed network, all of it is interrelated. All the nodes are counting for each other, things like that. I'm going to introduce this word called idiographic. So most of us, when we do networks, we probably end up with an aggregate network where we average across individuals. So we're doing 2 different groups. We average one functional connectivity network, compare that to a different average functional connectivity network. In contrast to that, we can have idiographic networks where just entirely person specific. So we don't consider anyone else. We just estimate a network for one specific individual. Obviously, that has some pros, and that's 100% precise to the individual. But when we do that, we also have some cons that we can't do some of the more typical group comparisons and inferences like that we're used to. And most of us, in most stats, almost all the stats we do are based on means, group averaging. And when we do that, this group averaging, we don't think too hard about it because we just kind of, this is how we're taught from basic stats, intro to stats. And really behind the scenes is kind of this assumption that differences across individuals are quantitative, right? That's just our sampling error, or our error. That's the variability. So we get a mean, we get a variance, we just assume that error is okay, attributable to randomness, and we move on. We don't think too much about it. And this is kind of how that looks, right? So we had 4 different individuals. They have this, they all have the same kind of path connectivity setup, but it just differs in the magnitude of the paths, the strength of the correlation. So they're qualitatively similar, but quantitatively differ, and we should attribute that to random error. And that's how I typically think about things. However, this kind of falls apart when we start thinking about heterogeneity. So the heterogeneity problem, as it's been dubbed by some people, is when we average across individuals, we presume that individuals are quantitative. However, and then the group average ends up representing the individuals. However, this doesn't quite hold if differences between individuals are not just random error, but actually qualitative differences. And as I'll point out, if there is substantial qualitative heterogeneity across individuals, the aggregate network ends up representing few, if any, of the individuals. And this is going to be important because if we have a group average network that doesn't really reflect anyone, any of the inferences we make using that group average network don't really end up reflecting the individuals. As a different way of thinking about it, if you average letters A, B, and C, what does that mean, right? You'd get some average letter, but since they differ in kind rather than degree, that average is kind of meaningless. And when you end up using that average model to compare something, it kind of doesn't make any sense. And this, again, to reinforce that, the real difference here is that we're thinking about individuals differ in kind rather than just degree. Supporting that here, we have 4 different networks, 4 different individuals with the networks that look completely different from each other. We get some group average network that considers all of this, but this group average network doesn't really look like any of the individuals. So sure, it is a group average, but it's not really too useful if you go back to thinking about the actual individuals. And this issue is termed ergodicity. So ergodicity is a statistical property where a group level model can be used for individual level inferences. The easiest way to think about it is group to individual generalizability. It has 2 main requirements. Ultimately, they both go to show that intra-individual variation is equal to the inter-individual variation. The first assumption, what we're thinking most about, is homogeneity across individual models, such that they do not differ in kind. The second one that we're not going to think too much about is stationarity over time. And that would be such that the network, if you kind of took different snapshots of the network at different time points, it would look pretty similar. A lot of work has shown that most psychological processes do not meet these criteria for ergodicity, even though we don't think about it too much. And again, a really important limitation is that violations do present valid individual level inferences. And this is a really critical limitation because ultimately, I think for most psychological or neuroscience work, we're thinking about individuals, not groups. But when ergodicity is broken, which it might be in most cases, we can't make valid inferences at the individual level. So in quantitative psych realm, this has been pretty well studied for a while. And Katie Gates, who did a graduate program under Peter Molinar, kind of listened to the field more largely, developed this program called GIMME to try to address these problems. So GIMME, Group Iterative Multiple Model Estimation, its goal is to create person-centered directional connectivity networks by explicitly accounting for inter-individual heterogeneity in kind. So it estimates group level networks that are not group averages, and we'll get to that shortly. And then on top of the group level network, it also estimates individual specific paths that contain both group level information and individual specific data. It's grown a lot, so now there's a lot of different options. You can think about multiple solutions, data-driven subgroups, confirmatory subgroups, and a lot more. GIMME is built on an SCM program called Extended Unified Structural Equation Modeling, and it's entirely data-driven. So here's how a GIMME group level model works, and we can see how it's different from group averaging. So in group averaging, everyone's going to get their own value for each different path, each different edge. We're going to average all those together and see if it's significant or not, essentially. GIMME is different than that because we're not really doing group averages. Instead, we're saying for a given path, let's say from A to B, each person gets 1 vote. 1 vote if this path exists or not. When you specify some a priori threshold, the default is 75%, and you say that if 75% of the individuals vote, yes, we have this path, then you add it to the group level model saying, okay, this path does actually represent the majority of individuals. So to example here, let's estimate a path for each individual. So all 4 individuals have this path, this up to down to up path. So since all 4 have it, it would probably make sense to add it to the group level model. So that's one model estimation process. Then we just iteratively do this over and over and over again until we get our final model. So let's do it one more time. So here we have 3 out of the 4 individuals do have this path. if our threshold is 75%, we would say, okay, that passes our threshold, so you would add that. We could estimate another. Here, only 2 out of the 4 individuals have this path. That's below our threshold, so we wouldn't add it. In real data, you end up getting a lot more paths. This takes a lot longer process, but it's kind of showing the highlight of how GIMME is built on it. Each person gets a vote, and if enough people vote that passes your threshold, then we add this to the group level model under the assumption that all of the majority of the individuals do have this path, so it actually reflects individuals, which is ultimately the goal.
Matt, can I ask a quick question?
Yeah, please.
Is this, so do the groups have to be identified a priori, or can you like use GIMME or like some previous stage to kind of parcelate groups based on like in this case like functional connectivity patterns, or like does it have to be like do you have to know the groups ahead of time essentially?
So the question being that could you get subgroups of individuals based on similar connectivity patterns, things like that, without knowing them ahead of time?
Yeah, does GIMME assume that you already know the groups that you're looking at before you run the model?
Let me get like 2 more slides up, and I might answer this question. If not, just ask it again. Okay.
Okay,
I think
sounds good.
this might be this might be the next slide. So, so at this point, what we're estimating here is a single group level model for the entire sample. So everyone we have, if it's MDD and control, doesn't matter. Everyone in that sample, unless you want to split them. The next part, which Rana might be getting at, is a subgroup level estimation. So here we finalize a group level model, right? We said these 2 paths are present for the majority of individuals. So we keep these in a group level model. And now we want to try to estimate data-driven subgroups. So these are subgroups that we're not specifying a priori. We have no hypotheses about what they look like. All we're doing is saying, do subgroups of individuals, maybe individuals 1 and 2 and 3 and 4, segregate into more similar connectivity patterns. And it's really kind of the same process. So we'd estimate 2 different paths. We'd say the first and fourth individual have this left to right path. The middle 2 individuals have this down to up path. And then we do this a lot more times in real data. Ultimately, we can use a community detection algorithm to test similarity between individuals and segregate them into 2 different subgroups, right? So now we're estimating data different subgroups based on individuals that are more similar to each other. Does that answer your question, Rana?
It does, yeah. So, but can I just clarify something? So these subgroup level models are derived from the main group level model still, right? So like whatever applied to the main group has to apply to the subgroups.
Correct, because we said that the group level, whatever threshold, I'm just going to say all for lack of a better term, all of the individuals do have that group level path. So both subgroups should still have that, but then they are distinct in these subgroup level paths.
Got it. Okay, thank you.
So like one of the cool things about GIMME, as we're kind of pointing out here, is that we get information at multiple different levels. So we get group level information, so all the individuals have this group level paths, then we get subgroup level information. Then once we finally finalize those subgroups, so we have subgroup A, subgroup B, we actually get individual level information as well. So here, 3 individuals, let's say individuals X and Y, the first 2 are both in subgroup A. So they have the subgroup level paths and the group level paths. Then we can estimate individual specific paths. Right, so all 3 individuals here have the same group level paths. Depending what subgroup in, they have their subgroup level paths. And finally, we estimate the individual specific paths on top of all of those models. So what we're ultimately left with is for each individual, we have a single model that contains shared information for the whole group. If we want subgroups, we can actually turn subgroups off. But if we want subgroups, we would also have shared information for that subgroup. We would have knowledge about which subgroup individuals are forced into. And then finally, we'd have individual specific information, and that allows us to better account for some of this heterogeneity between individuals. And we can do lots of different things with this after the estimation process we'll talk about later. So kind of rewinding this a little bit, just kind of quicker summary. So the first thing we did is we got our time series. So for fMRI data, right, we would get a time series for our different regions of interests. The more regions of interest you have, the more variables you have, the longer GIMME takes, the more complicated it gets. Most of the simulations have been tested with up to about 15 variables. So you get 15 different regions, give or take some. You get the time series from all of them. You would first estimate group level paths. Those group level paths are common to everyone. You then, if you wanted to find subgroups, you could cluster individuals into data-driven post hoc subgroups, so completely exploratory, no hypotheses. You'd get subgroup specific paths, and then for each individual, you end with a single path for them. And let's see if we want to talk about this. So behind the scenes, how this is working, it's all based on structural equation modeling. So how, when we say like each individual gets a vote if that path exists or not, that's using what's called modification indices. And modification indices are essentially questions of, would the model fit for a single individual improve if we freed a certain path? So if we add a path on for a certain individual, we estimate this relationship, would the model fit for that individual improve? So what GIMME is really testing is if we have a path, let's say from X to Y, would that improve significantly the model fit for at least 75% of individuals? If so, what's added on? That's at the group level. And then finally, at the individual level, we're only thinking about that single person. Would this improve the model fit for the single person? If so, cool, let's add it on. And I think that's kind of the main thing to know, that modification indices. And then once you go through the whole process, the final model is actually estimated from, so you have all these different paths that we estimated through these different iterations. And the final thing of it is we estimate a confirmatory model specifying the paths which identified in an exploratory way. And that just gives us some clean coefficients for each path we identified. So we ultimately end with a specific network for each individual. Okay. Let's take a pause there for any questions on the conceptual background for GIMME, why we're doing it, how it's working, different stages of it.
And so you're saying it can give directionality between the regions of interest, or is it just like these are related?
Yep. It will only give directionality. So all of GIMME networks will be directional. And there's been a recent paper about that. So the directionality is difficult, especially in fMRI, because things can be so noisy. And one of the things GIMME is built on, you can see here, if you look over here, we have these autoregressive paths. Because I mentioned that the directionality is based on range causality, which is considering the autocorrelation between each variable. In fMRI data, this autocorrelation can be very strong, especially as your TR shrink. So if like a lot of resting state data, your TR will be very small. You're getting lots of different scans very quickly, and that makes the autocorrelation very strong. And there's just like a lot of more complicated work of like the strength of that autocorrelation ends up affecting your ability to detect directionality quite a bit. A little more complicated than we'll get into today, but something to think about. Yeah,
Matt, just based on what you were just talking about with the shorter TRs, the autocorrelation will end up mucking up a bunch of things. But have folks relied only on like scan T to scan T+1 with short TRs, or have they looked at longer lags also?
Can you rephrase that question?
So the challenge with the autocorrelation with the short TRs is that you have such strong time T to time T+1 associations. Right. But some of the directional effects from one region to a different region might play out over a longer lag. So it could be a lag 2, a lag 3, a lag 4. Have any of the GIMME folks played with that in addition to just the lag 1?
I don't think so. And that's actually something I should have mentioned here. So probably all we were thinking about as I was talking through things are contemporaneous relationships, meaning occurring at the same time. But one thing Tom's pointing out here is GIMME can also estimate lagged relationships, meaning the effect of node X influences node Y, like 1 second later, 1 TR later, 1 time point later. And I think to Tom's question, GIMME is working on a lag of 1, so 1 time point. And I think that's all that's been tested to this point. I don't think people have tested longer lag times than that. Is that what you're asking, Tom?
Yep, that's exactly it.
Probably something that should be looked at. And so, for example, like we're talking about this like autoaggressive issue for like really short TRs, really short time points between really short intervals between observations. Like I'm aware of some people that have run into issues, for example, using GIMME with like ABCD fMRI data, where the TR is like 0.7 seconds. And I think they're just finding essentially no group level paths besides autocorrelations, because if you think about it, again, these paths are the variance explained after accounting for the autocorrelation. So if this autocorrelation is incredibly strong, meaning the measurement at T is like really close to the measure at T+1, you're gonna have almost no variation left over that can be explained by any of the variables. So people are thinking about ways to like downsample the TR and things like that.